So welcome everyone to the second iteration of our workshop, Frontiers of Neuromorphic Computing. Before we get started with today's program, we just want to say a few introductory words and organizational details. And Florian will start to talk about say a few words about the Institute.
Thank you, Clara. Welcome also from my side. On behalf of everyone at the Institute, I want to welcome you at the Max Planck Institute for the Science of Light. A few words about the Institute. First, about the Max Planck Society. So the Max Planck Institute of the Science of Light is one of 84 institutes of the Max Planck Society across all areas of the sciences and humanities. And by the way, this is a picture of Max Planck around 1900 when he made his important discoveries. So our institute really covers a very broad range of topics visualized by this gallery. We care about light from the fundamentals to its applications, from classical to quantum light. And very often we are working at the interface, at the fruitful interface between different areas. For example, linking optics and nanophysics, linking optics and biophysics, linking optics and condensed matter or information. At the Institute, currently we are 2 divisions. We are in the process of appointing new directors. Plus, we have this large set of incredibly creative, independent junior research groups. Some of you will have the chance to meet some of them during this conference, or maybe you already know some of them. And with that, I give back to Clara.
Good. So I think the other things we'll cover when we get to them. So we have quite an exciting program to look forward to with a lot of interesting talks. So I would say we dive in right away with our first talk today, given by Demetri Psaltis on optical computing, 2D or not 2D.
Thank you. Great to be here again. It's, I don't know how many times, maybe probably half a dozen. So we'll talk about optical computing. And the talk I'll give today is a talk I gave 2-3 months ago to a group that the National Science Foundation in the US, NSF, put a group together to explore whether they want to invest in this area and what to do. So they asked me to give a talk to the group. So the talk is like that, so I thought it would be appropriate for here as well. So I started by saying the first time I saw an optical computer was in 1980, and that was at Caltech, when I arrived at Caltech. And this is a synthetic aperture radar processor. It is a program called SARA, Satellite Imaging Radar. So what they did is they had a recorder, an optical recorder on the satellite, which recorded the radar signals on this piece of film. So that was another thing of the optics, because at that time there was no easy way to store all the data on the satellite. Then they would somehow have this film in a canister and eject it to Earth, or in the Pacific, and then a Navy ship could go pick it up and bring it to Pasadena, and then we would put it on this machine. And then back here was a camera, a Vidicon at the time, not a CCD, that would record the images. So these lenses, whatever, performed the linear transformation that was necessary from the radar signals, which is like an unfocused image, if you would, to the focusing. So that was very impressive, because I went there and I said, wow, because I had done my thesis already on optical computing, and I said, here's a working optical computer. And one of the very first things we did, an image of my hometown. This is Thessaloniki. So my high school is up here. The place where I grew up is around here. So this was very exciting to see a real optical computer. Unfortunately, it was the first and also the last one I ever saw. I didn't see another one working. Recently, however, there was a digital optical computing activity, but by and large, until very recently, the interest in optical computing has been hibernated. And now it's very, very hot. I mean, there's a lot of papers coming out, the companies large and small, raising a lot of money, investing a lot of money. And the reason is because of AI and data centers. So this is Jensen, the CEO of NVIDIA, or last year, I think, he announced the main thing he said was great about the new products was co-packaging optical chips with silicon chips. And it is a big step forward. So these chips didn't do much of computing, some, but mostly they were there to interface the clock of the inside of the GPU, which is like 2 gigabits, to the bandwidth from the fibers, which is hundreds of gigabits, or gigabytes. So this interface was done largely by these optics, but some computing, but very, very, very primitive. But nevertheless, there is a lot of interest because this story has been told a lot, that at the current rate of adoption, the power consumption and the power required for the computing is perhaps not sustainable with digital electronics, silicon. So people look at alternatives, including optics. So roughly 50 years of cold winter of optical computing. Not much happens. But SAR was static aperture radar was a great thing, but it was a very well suited for optics because the computation that needed to be done was a linear operation. Actually, linear operation that's very well matched to optics. And now data centers have already a lot of, because of the transceivers, they have a lot of optics already in there, and also the co-packaged chips that I just showed you. So there's a lot of interest again in optical computing. So AI is one reason. Another reason is because the toolkit that we have now and the toolkit that was available 50 years ago is drastically different. I mean, I showed you the SAR processor had a Vidicon camera. I don't know if most of you probably don't even know what a Vidicon is. It has, electron beams that are scanning. So no CCDs, no CMOS cameras, etc. A fiber optics telecom was a huge infusion of technology, modulators, detectors, etc. Perhaps this co-packaging in silicon photonics is the most significant. So we have a much richer toolkit now than we did then. Nevertheless, computing has been very, very difficult for optics. A lot of very smart people with a lot of money in companies and so forth have been trying to do this. And what has happened primarily is people have sort of pivoted towards communication, where it's natural for optics. And if I had to pinpoint two reasons why this has happened, one is everybody knows we don't have a high-speed optical transistor, which you need for the activation for the nonlinear part of neural network. So that has been pursued for all these 50 years, but it never materialized. The second, perhaps not as obvious, is that we don't have a large-scale optical memory. If you follow this domain, you'll see that the memory and the interface of the memory to the processor is now probably the most consuming part of the whole thing. So if we had an optical transistor and try to put a computer for an AI that does some of the computation, all this data from the database that trains, or all the weights and all that stuff that are stored in memory for pre-trained networks, how are they going to feed into the optical system? If they're going to be fed from electronic memories, then that's not going to be ideal. So for the rest of the talk, I had 4 ors, meaning 4 choices that we might have to make moving forward. And again, the spirit of this talk was, what will it take to have an optical computer that's actually adopted in the foreseeable future, if for no other reason, to at least maintain the momentum. Because a lot of money has been invested. I don't know how many, somebody said something like 23 Nature papers have been published in the last couple of 2-3 years. There's a lot of interest, a lot of activity. But it'll collapse unless there is an adoption. So these are the 4 ors. How do we do the activation function? How do we make decisions? If it's just linear, I think it's it's not going to be good enough. A lot of the activity has been on linear accelerators, but if you really want to have a full optical computer, you need the nonlinearity. So you can do this with nonlinear optics or OEO, optics, electronics, and vector optics. I think there is I wouldn't call it fundamental, but a persistent trade-off between power efficiency and accuracy. If you want optics to do things very accurately, usually it means you have to have digital optics or something like this. You pay the price in power. So then the question is that, will you go for power efficiency or accuracy? Training, do you train the network in the optical domain, or you just work with sorry for the dyslexia, adaptive, or you work with pre-trained networks. And the 2D or not 2D, which is, do you work with this integrated or free space optics? The not 2D is the free space optics. So I have a comment for each of these, and then I'll sort of vote what I think is the most likely thing. The vast majority of architectures that have been demonstrated so far, recently I should say, can be fitted into this kind of diagram. This is from a paper we wrote recently with colleagues from BFL. It's an opinion paper about exactly this topic. How do you do the activation function? The way it's done now, you have some input on an SLM or some modulators. It goes through some linear optics, and then it's OEO, the detector. Electronics is the red part, so it's the bad thing. And then modulator again, somehow, back in the optical domain. And we do this multiple times, and then get the output. Then the training, again, by and large, I would say almost always, is done through electronics. So you update what the way it should be in electronics, and then somehow you enter them through modulators into the optical system. So the question is, should we replace this part here with nonlinear optics to do soft thresholds or maybe softmax or some other operations that normally are done? So the conclusion from this paper was not really. And the reason is the optical power needed for the nonlinear optics and the lack of materials make it very difficult. It's possible to build some sort of network to do something, but and publish a nice paper and so forth. But in terms of adoption in practice, if the goal is to build a system that will reach use, actual practical use, I think what we argued here was OEO is the answer. A related topic is the second one, which do you try to optimize power efficiency or accuracy? Which roughly means, do you stay in analog all the way, or do you convert to digital at some point? Because converting to digital is because the A to D conversion takes a lot of power. So that's if you have to go digital, then it's a problem. So in this paper, again, this is the same paper, we had the energy budget based on papers we found in the literature. So these were the best we found. It could be, one can argue they can do better. But the point is that if you look at analog OEO, it's one order of magnitude, if not two, more power efficient than nonlinear optics or digital OEO. So digital OEO is as bad as nonlinear optics, if not worse, because of this A to D conversion. So the argument here was that we're better off with staying analog all the way, using analog electronics in the in-between, and then going very fast. Okay, so there's another way to do the nonlinearity, which is with polynomial expansions. This Hui Kao, who's here in the front row, or second front row, came up with this idea called structural nonlinearity. The idea is if you want to have an input, which is a dog in this case, if you modulate a beam, a laser beam, multiple times with the same input, then you get for two times you get the square, 3 times you get x cubed, etc. Or you can do square law detection, which is also some form of polynomial expansion because you get the cross products. So if you do this sort of thing, then you have the output being a linear combination of different orders. And in free space optics, people do this a lot, including ourselves. This is from our own work. And Hui has done it as well. And Aydogan Özcan, he does it a lot. He uses primarily this square law detection. So that's another way which avoids entirely the need for anything, because you do everything with linear optics, and you just do this trick of multiple presentations or square law. In my experience, this is interesting, and you can get nice results and nice papers, but I don't think the performance that we have, at least we have been able to get with this sort of approach, is competitive with large-scale digital LLM, digital models. Maybe just a question of finding the right way to train this type of network or something else. But you can get nice results. Like this is published in Nature. At that time it was in Archives, but now it's been published in Nature Photonics. So you can get nice results, but I'm not sure you can catch up with the digital architectures. So for the activation, OEO, analog OEO is probably the best. Now, a neural network needs to be trained. In other words, you have to present examples and fix the parameters somehow to minimize some sort of energy function. So in early work in 2011, then we used to do this in nonlinear crystals, photorefractive cubes of crystals whose properties would change when light hit them. So we would record holographically through phase conjugation, and we were able to map error backpropagation or gradient descent into the evolution of gratings in photorefractive crystals. It was extremely exciting. Very nice, smart people got nice PhD thesis out of this. But it was very difficult, really, to make a system that was working. This is, on the other hand, in terms of fixed memories, fixed optical memories, this would be an adaptive optical memory. It's 3D storage. 3D storage for in glass. Several people, including this company. This is a startup, I think, out of Duke. What they claim? They claim, they say 5D, don't worry about that, 360 terabytes into a 5-inch glass disk. So that's kind of interesting, because if you have all these terabytes into a single glass disk that can last forever, so if you have databases there, or you have the pre-trained weights, now you can imagine feeding a monster, an optical monster that does computation very quickly. So something like this is, to me, much more interesting than trying to find the nonlinear material to store all the weights, at least for the foreseeable, for the close future. Okay, the 2D or not 2D. I see Dirk there in the back, looking at his upcoming talk. So him and Marin did this, kickstarted this iteration of optical computing by publishing this paper, extremely impactful paper. And this is a 2D, doing MZIs, Mach Zehnder interferometers, or resonators, whatever, different ways. You can synthesize a linear operator, and even some cases people do also nonlinear. But this is done by lithography, similar techniques as silicon and so forth. So this is more scalable, more robust, etc. There's a lot of work, including our own, on free space. It means you have different diffractive layers. Some of them are fixed, some of them are modulators, special light modulators. And then by modulating the different layers and having some free space propagation in between, you can construct linear operators and then find a way to build the nonlinearity as well. So this is the first paper I remember saying is from Chong-Chai Dai, Professor Dai, who has this huge group in China. But also, we do stuff like that, but a lot of people, I should mention, Aidogan Özcan again, has a lot of contribution. Now, if you are to compare these two, you might look at operations per second. And you say, okay, assume we do analog OAO here, and we do fixed weights that are trained, how fast can we write something like this? So with 2D, you can imagine having an array of 1,000 inputs, not a million, because just on a single chip. But you can go at extremely high rate. You could go maybe to 100 gigabits or more. And then if you assume a fan out of 10 to the third, you can easily argue that the operations per second are huge. Whereas in 2D, if we rely on current SLMs that are, this is 1,000 frames a second, which the DMD devices can reach, then you become limited, even if you claim that you can fan out by a lot. So this idea that going to 3D, we have more computational power, is mitigated or counterbalanced, I would say, by the fact that it's much easier to introduce very high-speed modulation through this lithium niobate, these thin devices, or VCSELs even, the different modulator devices to enter data and process it at higher speed. Okay, so I forgot that that Dirk was going to be here, but this is a copy from one of Dirk's papers. One way to get around this problem and still work in 3D would be to do this co-packaging of the SLM and the CMOS detector. And also, you can imagine this being optically addressed. When I was young, we used to have this optically addressed specialized modulators, which you cannot find anymore. There used to be a photosensitive layer and a liquid crystal device, or something called a PROM with an electro-optic device. Here, you would just modulate fast through the interface, direct interface pixel to pixel with the silicon. So in Dirk, I think, if I read his paper correct, he was predicting a gigahertz bandwidth, I mean, 1 billion frames a second, and 1 million pixels in parallel. So this would change this picture. It would make free optics, again, perhaps a little more. Now, if you go to TD or not 2D, the very first thing we did in '85, just a little bit after Max Planck did his this thing, we built this is the Goodman version, and then this is the one we drew, to build a Hopfield model. And this is not really, looks like a 3D because it has free space and so forth. But in reality, at around the same time, 5 years later, David Brady and I, David Brady was my student at the time, some of you may know David, he implemented actually on a chip, on a 2D waveguide, a vector matrix multiplier. And interestingly, we could program it from the outside, from the top, but the inference would happen on the inside. So the 2D and 3D are not really that the distinction, because even the co-packaged chips, is that 2D or 3D? Very recently, just like a few weeks ago, we submitted a new paper on the same architecture, looking at this thing. That's David and I, and then Andre, which is a guy that did some of the coding. And our argument in this paper was that if you do the weights in discrete devices, MZIs or whatever else, versus doing them with holograms, you get an advantage of square root of n, where n is the number of input elements in the vector. And intuitively, the reason you get this is because the information for what is the weight of the connection between an input port and an output port is distributed. So if you superimpose many of those weights, which can be separated because of the Bragg selectivity, they don't add up coherently, they add up incoherently. So it goes a square root of n, and you get this advantage. So you have, so if n is let's say 100, you can have a chip that's scales is 10 times better. What's more, the voxel, or the size of its weight for the hologram is very small. It's less submicron, order of a wavelength. Whereas here it's normally bigger. On the other hand, you know, here we're doing these things in silicon or very well-established technologies. Here we're still looking for a material. The way we're pursuing it is with 3D printing for fixed holograms. Okay, so now this is kind of the bringing it home. The 4 ORs. For inference, I probably gave it away already. I definitely believe OEO is the way to go for the foreseeable future. For the next step. There we need help, like the thing that I showed you from Dirk's lab, where you detect and modulate, definitely not without the digital. Power efficiency versus accuracy. I mean, those of you that have worked with analog systems know that it's very, very, very difficult to make, you know, even 8-bit or definitely 10-bit accuracy machines. The question is it worth trying for that? And if you sacrifice power efficiency, I would say not. And neural networks are inherently tolerant to some inaccuracies, but yeah, this is my last slide. So I would say then hopefully you would get some error correction downstream and live with limited accuracy in the optical domain and get the power efficiency. Training, for sure I would say fixed. I don't know of any technique that's adaptive. People talk about these phase change materials for MZIs or something else. But if they're thermal, it's not good. But hopefully something will come up there. But I think there's a lot of room to do stuff with fixed. And 2D or not 2D, again, I probably gave my vote away. Anyway, so that's all.
So thank you very much for that great talk, and also for absolutely staying in time, which is important because I think this talk invites a lot of discussion. Who wants to ask the first question or comment or objection? Dirk?
Uh-oh.
Yeah, thanks for the great talk. There's a microphone. Amazing.
Okay.
Yeah, thanks for highlighting our work on the thin film lithium niobate 2D modulator array. And the problem there is to get the data to be processed. So you go, just to modulate these devices at high speed. Not enough electronic I/O to get to that kind of scale. And so I thought it was interesting that right before that, you mentioned that there were SLMs that you could optically program.
In the year 25 minus, no, in the year of Max Planck, yeah. In the 1980s, yeah, there were. The PROM.
Exactly. So actually, so EPROM is awesome. Do the young people here know what EPROM is? All right, this is super cool. I try to get my students to get into EPROM, and I haven't succeeded yet. But it's an example where I just want to second your point that if you could have something like an EPROM, which is it uses a photoconductive material to program an electronic state in a memory, then you don't need to get out to the periphery for processing. Stay in line. And so there are many of these opportunities that I think are super important to investigate. And I don't know. I think if one had that, it could make a big difference. And this was an attempt at this. But I think through this workshop, we'll have a chance to talk through many more of these. But yeah, check out EEPROM and put that into SLM, please. High-speed SLM. That would be really cool.
Yeah, but just I couldn't agree more that this would be a huge benefit if these are available. But if you think about what might enter a working machine in the next, let's say, 5 years, it's much more likely to be high-speed modulators coming from a fiber array. You can have modulators on one place, and the fibers converging as an entry to the optical system. And if you have just 100 of those, now you can have the transceiver, you can have a huge data rate coming in. And these devices can be in the hidden layers, and then eventually may also be in the input layers. So I think I appreciate your work, and I also appreciate the spirit of the work that an optically addressed SLM high speed would be a huge break for us working in architecture, because now you can you can draw more architectures. But in terms of building the next machine that may be adopted by data centers, I think it's more likely to be what's available kind of now.
I think Logan.
Hey Logan, did you sleep well?
Did. One quick thing, correction. There are still optically addressed SLMs that are available. There's at least one company that still sells them. My question is,
who's that?
I'll tell you later. I don't remember the name. But we talked to them before, and it's a photoconductor, just like the previous ones were.
Like Mingu's company, you know, Mingu is a billionaire now from having something like you might call an optically addressed SLM, you know, a photoconductor interface. Yeah.
Although this one wouldn't go fast enough. But my question is, so your talk didn't talk at all about applications of optical computers outside of the data center. And without revealing my opinion, I'll say that many people in the community are really, talking a lot about, edge-facing applications. I guess I'm curious, do you have an opinion about this? Do you think there's an opportunity there? Is there a reason that you ignored it, or do you think it's like a whole different thing?
Well, I think I've told you what I partially think. I think it's a cop-out to say, well, you can use this stuff, to do some image processing or something else. Because, that's where the real interest, people invest billions in these startups. IR just raised $500 million, right? Because they do the scope package chips, not because of edge, right? And also the reason we get all this funding in our labs and the Nature publishes our papers is not because of the edge things. An edge thing, if you have, it'd be hard pressed to publish it in Nature Photonics, right? You have to go to optics letters or something. So what drives this current wave is AI in the data centers. Having said this, if there's something to be done with this kind of techniques that emerge out of this activity at the edge, fantastic, we just take it, right? But it's not, particularly the reason I put this talk together, which is to advise this NSF thing. So, yeah, if it's there, take it.
You said something about neural networks tolerating some inaccuracy.
Yeah.
Be a little more specific about that, because the way I understand it is that often comes from, say, training quantized neural networks where you use fewer bits, but a couple digital bits and analog inaccuracy are super different. And the problem with putting things into analog is often that these errors compound. So could you just comment on that? I don't know if...
Yeah, in the digital domain, what people do is try even going down to 2-3 bits and showing you can get good accuracy. And people, one of them is in this room, right in front of you there, Logan, and McMahon have done experiments with few photons, etc. Even down, that's not directly an accuracy thing, but clearly, if you have 1 photon per weight, that's a quantization error of some extreme. You know what I'm talking about.
I do, but quantizing in a digital system is very different than analog error, which can then compound in a very different way.
Okay, how is that different? Maybe you can teach me something.
Sure. So the digital quantization, right, is completely deterministic. It'll work the exactly same way every time. And so when you optimize on it, the optimizer can take advantage of that consistency. Whereas when you're implementing a chip in real life, you don't know whether it's going to round up or round down. And if you have many layers, that error will propagate. It's a big problem in making big analog systems. I'm just wondering if that's the type of error you meant, or just.
Well, okay, I'm not sure I know what you mean, but I do know the following. In the optical systems that we try to build, and several, the main problem is not accuracy, it's drift.
Okay, I consider that part of accuracy, I guess. That just anything that's not matching your model.
Yeah, so I mean, if there's no drift, I mean, while usually there's like, let's say there's a couple of hours of no drift, then the learning and the sum and all that stuff takes care of it. Now, the accuracy that you have is in a digital twin, mirrors the accuracy that you get in the experiment, and that stays. What falls apart is when it starts drifting. So that's, if you call this inaccuracy, that's the problem. Digital don't have this. Yeah, generates maybe some error and so forth. So I would say stabilizing or continuous online training or some way to adaptively track the drifts is, I would say, the most immediate problem, not the accuracy.
Thank you.
Thank you very much. I think in the interest of time, we finish the discussion here and thank Demetri again.